Have you ever just stopped and thought about all the invisible forces at work around us? And no, I'm not talking about magic, but something, well, just as powerful, really, the physics of fluids. I mean, from a massive ship floating on the ocean to the brakes that stop your car, we are constantly using these simple principles in some pretty incredible ways. So let's pull back the curtain on these invisible forces and see exactly how we put them to work every single day.
Seriously, think about it. How is that even possible? You, with just a simple push of your foot, can generate enough force to bring thousands of pounds of moving metal to a dead stop. There's no extra engine kicking in, no complex electronics doing the heavy lifting. It's just a simple, almost beautiful principle of physics. And trust me, by the end of this, you'll know exactly how it works.
And here it is. This is the answer all laid out in one diagram. It's a hydraulic brake system. Now, I know at first glance it looks kind of complicated, right? You've got the pedal, all these tubes and cylinders at the wheels, but the core idea that makes this whole thing work is surprisingly simple.
Okay, so before we can really get into how to multiply force, we first need to understand something fundamental about all fluids. They push back. This upward push has a name. It's called buoyancy, and it's the entire reason some things float while other things, well, don't.
The best way to think about it is like a constant battle. You've got gravity, which is always pulling an object down with a force equal to its weight. But at the exact same time, the fluid it's in is pushing it up with that buoyant force. So, if the weight is greater than the buoyant force, it sinks. If the weight is less, it floats. It's that simple. It's just a little tug of war that decides what happens to every single object in a fluid.
And this is a perfect example of a really crucial point. That buoyant force is always there. It's not just for things that float. Even this super heavy anchor gets a little bit of a lift from the water. So why is that? Well, it's because pressure in a fluid gets stronger the deeper you go. That means the water is pushing up on the bottom of the anchor with just a tiny bit more force than it's pushing down on the top. The result is a small but constant upward lift.
Now let's get to the real secret sauce behind our car brakes. Back in the 17th century, this brilliant mind, Blaise Pascal, he discovered something truly game-changing about how pressure works inside a contained fluid. And honestly, this one discovery is the foundation for pretty much all of modern hydraulics.
Okay, so what does that actually mean? The most important part is this. If you have a fluid in a sealed container, think of the brake fluid in your car's brake lines, and you increase the pressure at any single point, that exact same pressure increase is felt instantly and equally everywhere else in that fluid. It's like a perfect communication system for transmitting force.
And this is how we take advantage of that principle. What you're seeing here is a basic hydraulic system. You've got an enclosed fluid that connects two pistons of different sizes. So when we push on that smaller piston, we create a change in pressure that gets sent right over to the larger piston. And, you guessed it, this is where the magic happens.
This simple little equation is everything. Pascal's principle tells us that the pressure, which is just the force you apply over a certain area, has to be the same on both sides. So if we apply a small force to the small piston, the fluid transmits that pressure over to the large piston. But here's the kicker. Because the large piston has so much more area, it has to push up with a much larger force to keep the pressure the same. It's basically a loophole in physics that lets us multiply our effort. Okay, theory is great and all, but let's see what this looks like with some real numbers. Because we're not just talking about a small effect here. We are talking about huge, massive gains in force from a pretty small input. Right, let's take the classic example, the hydraulic jack, or maybe the car lift you see at your local mechanic shop. How in the world does a mechanic lift a heavy car with what looks like almost no effort at all? Well, they use a system that looks just like this. A small force gets applied to that narrow piston. That creates pressure in the hydraulic fluid, which then travels over and pushes up on the wide piston that's sitting right under the car. And because the area of that wide piston is so much larger, the upward force it creates is absolutely enormous.
Let's actually use some numbers so you can see just how powerful this is. Let's say we push down on the small piston with a force of 500 newtons. To give you some context, that's like pushing with about 110 pounds or 50 kilograms. It's a solid push for sure, but definitely something a person could do.
Now let's say the large piston under the car has an area that's 20 times bigger than the small one. Well, because the area is 20 times larger, the output force is also 20 times larger. Our 500 Newton push magically becomes a massive 10,000 newtons of lifting force. That is over 2,200 pounds. We just turned a manageable push into enough force to lift a car, all thanks to Pascal's principle. Okay, now we have all the pieces of the puzzle. It's time to go back to our original mystery and put it all together. Let's solve it. How does that tiny push with your foot stop a 2-ton car?
When you press that brake pedal, you're applying force to a small piston inside the pedal cylinder. And just like we learned, Pascal's principle says the pressure you create is sent undiminished, equally, through the brake fluid to the larger pistons in the wheel cylinders. Just like the car lift, this multiplies your force, creating an absolutely immense clamping force that presses the brake pads against the spinning wheels, stopping your car safely and effectively.
So we've seen the incredible power of fluids when they're just sitting still. But what happens when they're moving? Well, it turns out there's another really elegant principle at work, one that shows us this fascinating trade-off between how fast a fluid is moving and the pressure it exerts.
So, just take a look at this pipe. The fluid is flowing along, minding its own business, and then it hits this narrow section, a constriction. Now, in order to get the same amount of fluid through that narrow part in the same amount of time, the fluid has to speed up. That makes sense, right? It has to rush through the smaller opening. But here is the wild part, the discovery we call Bernoulli's principle. Where the fluid is forced to speed up in that narrow section, the pressure it puts on the walls of the pipe actually drops. And back in the wider section where the fluid is moving slowly, the pressure is higher. It's a completely inverse relationship. Fast-moving fluid equals low pressure. This one idea is fundamental to how airplanes fly, it's how a wing generates lift, and countless other technologies.
So let's wrap this all up. We've seen that fluids are always pushing up on objects with a buoyant force. We've learned the secret to all of hydraulics, Pascal's principle. The idea that pressure changes are transmitted equally everywhere in an enclosed fluid. And we've seen how we can use this to build simple machines that multiply our force to do incredible things, like lifting a car or stopping it dead in its tracks.
These principles are just so elegant, so powerful, and they're operating all around us, mostly unseen. It really makes you wonder, what other powerful, invisible forces are out there, hiding in plain sight, just waiting for us to understand them?